So once we have the overall potential values for both the anode and the cathode at the current density that we want, we set current density of 1000 ampere meter square electrolytic cell. Then we can calculate the cell potential. Galvanic cell potential would be equilibrium potential, cell potential minus the loss contribution from anodic polarization or overpotential at the anode, overpotential at the cathode, and the ohmic loss, the current times the ohmic resistance, primarily from the electrolyte. Okay, so let's first look at the ohmic potential loss, which is current times resistance. And the current would be J times A, current density, times the area. And the resistance, if you learn in physics, would be resistivity rho times the length of the conductor divided by the area of the conductor. Okay? And then resistivity would be 1 over conductivity. So this ohmic loss, the potential loss due to ohmic resistance primarily in the electrolyte would be current density times area absolute value 1 over conductivity times length divided by area. Of course, area and area would cancel out. And so without the potential loss for ohmic part would be conductivity absolute value, which is just conductivity times the length of the electrolyte divided by conductivity of the electrolyte. Now let's plug the number in. The absolute value for current density would be 1000 amp per meter square. Length we said is 2 millimeter or 0.002 meter. Conductivity we said for electrolyte is 60 Siemens per meter. Okay, so this per meter in the denominator and the meter together would be meter square and cancel out with this meter square. As a result, we would have plug the number 1000 times 0.0022 divided by 60, we would get 0.0333 in the unit of amp per centimeter. And remember, not centimeter, Siemens. And Siemens would be 1 over ohm. So amp divided by 1 over ohm, essentially 1 amp times ohm. Amp times ohm would just be volt. So the voltage loss comes up to be 0.0333 volt or 33.3 millivolt. That would be the potential loss due to ohmic resistance primarily associated with electrolyte, 33.3 millivolt of loss. As a result, the overall galvanic cell potential would be 1.74 volt, which is the equilibrium cell potential when there's no current, minus absolute value for the anode or zinc electrode, which is absolute value of 0.0373 volt, plus the contribution of the cathode. We said the cathode over potential is minus 0.1439 volt or minus 143.9 volt, but you take absolute value. And finally, the ohmic loss. Absolute value, and ohmic loss, also absolute value. And in the end, the cell potential for this galvanic cell between zinc hydroxide and the nickel oxide hydroxide and nickel hydroxide is 1.526 volt under the specified current, galvanic cell current of 1000 amp per meter square. Okay, so we got the cell potential for the current density that we want.